Let's work through our homework problem by using our steps that we outlined already. Got two charges. I'm going to call them Q1 and Q2. And I'd like to find the electric field at the top of a triangle. I know the sides of the triangle and the magnitude of the charge. Q1 is positive, Q2 is negative. My step number one is to draw the electric field vectors at point P. So Q1 is a positive charge. Start my pen at point P and I go away from Q1. So there's my electric field vector E1. Draw my electric field vector E2. I put my pen at P and then I go towards my negative charge. There's my E2. All right, so there's my vectors drawn. Step two is to find the magnitudes of the charges, the magnitudes of the electric fields. So my magnitude of electric field E1 is K times the magnitude of my charge Q1 divided by my distance R1 squared. R1 is from my charge to my point P, so R1 is equal to D. So that's 8.99 times 10 to the 9 newtons meters squared over coulombs squared, multiplied by my magnitude of charge. It says Q1 is plus Q, so the magnitude is 1 microcoulomb. 1 times 10 to the minus 6 coulombs, divided by my distance. My distance is 1 millimeter. Don't forget to square your distance. Gives us a magnitude of electric field E1, 8.99 times 10 to the 9 newtons per coulomb. That's just the magnitude, that's not the direction. Next step is find the magnitude of electric field E2. Now E2 is interesting. That's K times the magnitude of Q2. That's 1 microcoulomb times the magnitude of distance R2. So R2 is from the point to the charge. That's also D. Magnitude of Q2 is the same as the magnitude of Q1. So what that tells us is that E2 and E1 have the same magnitude. 8.99 times 10 to the 9 newtons per coulomb. Okay, next step is to find our x and y components of our electric field. So E1 has an x component that points to the right. I'm going to take positive x to be right and positive y to be up. It has a y component that points up. So I've got E1x and E1y. For my angles, it's an equilateral triangle. So this angle is 60 degrees. So this angle is 60 degrees. Let's find my components. E1x is adjacent to my angle, so it's E1 times cosine 60 degrees. That's equal to 4.495 times 10 to the 9 newtons per coulomb. My E1y is opposite my angle, so that's E1 times 60 degrees. That's equal to 7.786 times 10 to the 9 newtons per coulomb. Okay, what about E2? The x component of E2 points to the right, that's E2x, and my y component points down, E2y. My angle, since this angle is 60 degrees, this angle is also 60 degrees. Okay, let's use that to find my components. E2x is positive, so it's plus E2 cosine 60, it's adjacent to the angle. 4.495 times 10 to the 9 newtons per coulomb. My y component points down, so it's negative. And it's opposite the angle, so we use sine. So we get minus 7.786 times 10 to the 9 newtons per coulomb. As you might have guessed from your diagram, the y components are going to cancel and you're going to be left with an x component only. So the vector sum is E equals E1 plus E2. So the x component is the two x's added up. That turns out to be 8.99 times 10 to the 9 newtons per coulomb. Our y component is the two y's added up. That turns out to be 0. Then we finish by writing our answer as a vector, which is 8.99 times 10 to the 9 newtons per coulomb I hat. If you go back and you compare this against doing it the short way, which is that electric field is force over test charge, which we did earlier, you'd see that we get the same answer. So for this homework problem, we've got 4 charges on a 1 centimeter square. I'm going to call them Q1, Q2, Q3, and Q4. You might notice that we've already done this problem the short way. Let's go through and do it the long way now by doing the vector addition. Let's find the electric field at the center of the square by using a vector addition. So I'm going to put my point P at the center of the square. There is no charge at point P, it's just an empty little bit of space. Okay, I'm going to start with step 1. Let's draw my electric field vectors. So my electric field due to Q1, I know I have to put my pen on top of point P and I have to draw away from Q1. So that's my first electric field vector, E1. Likewise for Q2, put my pen on top of P and go away from Q2 because Q2 is positive. There's E2. Now for Q3 and 4, Q3 is negative, so I have to put my pen on point P and go towards Q3. That's E3. And last for Q4, I put my pen on point P and I go towards Q4. There, a little bit of a mess, but hopefully you get the idea. All of those vectors are on the diagonal of the square. Okay, next are my magnitudes. So the magnitude of electric field vector E1 is equal to K times the magnitude of my charge Q1 divided by my distance R1 squared. R1 is from Q1 to point P. Draw that one in a different color, R1. So R1 is a half the diagonal of the square, or you can do your Pythagorean theorem. So I've got 0.5 centimeters on this side, 0.5 centimeters on this side. So R1 is equal to the square root of 0.5 centimeters squared plus 0.5 centimeters squared equals 0.707 centimeters. Okay, go ahead and put that in the equation. K is 8.99 times 10 to the 9 newtons times meters squared over coulombs squared. Q1 is the magnitude of charge that's given as 1 microcoulomb, so 1 times 10 to the minus 6 coulombs. Divide that by R1 squared, 0.707. Make sure you put it in meters squared. What we get for that electric field magnitude is 1.80 times 10 to the 8 newtons per coulomb. That's the electric field strength due to charge 1. If we look at our charges, all 4 of them have the same magnitude. They're all at the center of the square, so they all have the same distance. So the magnitude of each electric field is all going to be the same. So E2 is equal to E1, and that's also equal to E3 and E4. Okay, next step, we want to find the components of those vectors. I'm going to go on to a fresh slide just so we get a nice fresh diagram. So there's the center of my square, there's Q1, there's my electric field E1. So my x component goes to the right. I'll take positive x right, positive y up. My y component comes down. So there's E1x, there's E1y. I'm on a square here. The diagonal of a square is on a 45-degree angle. So this angle is 45 degrees. So E1x is adjacent to my angle. I'll use E1 times cosine 45 degrees. Plug in that E1 was 1.80 times 10 to the 8 newtons per coulomb times cosine 45 degrees. Gives me my x component of E1 to be equal to 1.27 times 10 to the 8 newtons per coulomb. For my E1y, I see that my y component points down, so it's going to be minus E1 times sine 45 degrees equals minus, squeeze in my minus sign, minus 1.8 times 10 to the 8 newtons per coulomb times sine 45 That gives me a y component of minus 1.27 times 10 to the 8 newtons per coulomb. Next, we have to find the x and y components of the other three vectors. For my other components, I'll take full advantage of the symmetry. E2 has an x component that points left and a y component that points down, so E2x is minus E2 cos 45 equals minus 1.27 times 10 to the 8 newtons per coulomb. The y component points down, E2y equals minus E2 sine 45 equals minus 1.27 times 10 to the 8 newtons per coulomb. If at this point you recognize that E2 and E3 were identical to E1 and E2, you could go ahead and write those components, or you could go ahead and calculate them. So E3x points left, minus E3 cos 45 minus 1.27 times 10 to the 8 newtons per coulomb. The y component points down, so minus E3 sine 45 and then for E4, E4x equals, I don't have quite enough room, so I'm just going to say equals E1x equals 1.27 times 10 to the 8, and E4y is the same as E1y. It's minus E4 times sine 45. Okay, now we do our vector sum. So EX is E1x plus E2x plus E3x plus E4x. If you add up all those x components, so this guy plus this guy plus this guy plus this guy, you're going to get 0 for your answer. Our y component, EY, is all of our y's added up. If you add up all those guys, what you get for your answer is 5.09 times 10 to the 8 newtons per coulomb. Had you said that your net EY was 4 times E1y due to the symmetry, that would be okay too. And then your total electric field vector, you have to write as a vector, so that would be, oops, I dropped my minus sign, sorry, it's minus 5.09. Minus 5.09 times 10 to the 8 newtons per coulomb in the y direction, j hat. If you check back against when we did this to short way, you should see that we have the same answer.